this is the final video for the Table Tennis Trainer 2 team. So gonna run through the final design for the arm, things we've changed since the last video, and then next steps for future years. So for one, the largest piece that we've been developing over this capstone project is the physical arm itself. As you might remember from last video, we have kept the same general structure and motor configuration. So there are 5 degrees of freedom of this arm: rotation around the base, rotation around the upper arm, forearm, and then 2 motors that control the paddle movement. The 3 larger arm joints have stayed the same since the last video, but one of the larger modifications we've made in the second half of the semester, it's switching out heavier 5010 motors for these smaller servo motors. This was primarily because while the 5010 motors were incredibly strong, they were also very heavy, and they greatly increased the moment of inertia of the arm as it was moving. This was the older version. Obviously you can't tell, but this is very heavy compared to the lighter version we have now. And we saw often that the motors for the smaller, more base parts of the joints were slipping when the arm was moving out. So we switched over to this just to be a little bit more efficient. We've also updated and created a full base. So this is freestanding. It's able to support the arm in any movement that we have. We also have a full wiring configuration here that fully commands the arm. Unfortunately, during travel for Showcase, the motor that commands the base rotation was damaged, and it sometimes can lose its position and get unstable and fly around, but we won't have it on right now, but shortly in a second I will include videos of the demonstration working.
It was just backwards.
Where we've left this project is currently from the sensor team, we receive an XYZ coordinates relative to the base and the table of where to intercept the ball. On our side, we've created an inverse kinematic model of this arm that translates that 3-dimensional coordinate and turns that into 3 joint rotations for the base part of the arm to move over to that point. I did say 3 instead of 5. That is because the 2 motors that command the paddle, we have set to automatically move relative to the table. So you'll see in the demonstration video, but this arm will always move and this paddle will always move relative to where the center of the base is, to make sure that wherever the ball is intercepted, it has an open face going to the other end. This was the simplest configuration we found to return the ball reliably. One of the larger projects for next year's team is to make a more consistent return, which I'll talk about later, but that is how we physically move over there. You'll see throughout our testing that we were able to semi-consistently hit the ball with the pad of the paddle. That was a big success for us. We unfortunately closed the project without being able to fully return the arm, the ball to the other side. That is primarily because the motion to physically return a ball requires basically a full reset of all of the movements and configurations for how the arm moves after that point. Because up to now, we've only been focused on trying to intercept a point in space instead of trying to push back relative to that point. But we were very happy with the success that we've had. As a reminder, the main purpose of this year's capstone was to make a base set for future years to work off of, and also get to a point where we can semi-reliably track the ball and semi-reliably return it, which is something we have more than exceeded. So next steps for this project for next year, for one, like I mentioned earlier, one of the largest steps that's still needed is to create a full return trajectory. We planned out a few quick fixes of having the paddle just flick out whenever it intercepts the point, or just having it constantly flicker up and down just to be a little bit more consistent with hitting the ball. Through testing, we found that that wasn't as consistent as we'd like it to be long-term, so there will likely need to be a full redesign of how you actually return the ball. There are also some minor mechanical configuration changes that could be made. We believe that the setup for the arm itself is well made, but there could be expansions to the belt reductions that we've used. We've seen through a few tests that we were able to track and move over to the ball reliably, but we weren't able to intercept it simply because the fidelity for the motors weren't accurate enough to actually hit the point we expect to. So we've oversized some of these motors, so we should have enough power and speed to account for any added reductions onto that. And then finally, there are some adjustments to be made on the inverse kinematic model to make it slightly more accurate based on the mass and moment of inertia of the arm.